picking it up here. This will be the last little bit going through that exam. Again, remember, these are really the basics of converting between x, y, and z to r, theta, and phi are really of the order of calculation of 126 plus 453. And many of us have a hard time nowadays adding those together or multiply them, but learn how to do these conversions and regularly do the conversion also to this idea of a magnitude times a unit vector, because the unit vector is going to be the thing that really describes a direction, and you've been using it, believe it or not, since you started drafting in CAD. So we have gone all the way through, in essence, all the way through the problems 1 through 13, and the last one, a distributed load. I'm going to go here once again to a new slide here. A distributed load, if you would, is, and we're coming upon this right now, distributed load is essentially, if you think about a distributed load here, maybe that's a distributed load, it's essentially a parallel force system, so a parallel non-concurrent. Now a distributed load is not always straight up and down. A distributed load could be a wind load. So it might look something like this. That's a distributed load, right? It could be gravity on a cantilever. It could be a gravity on a cantilever and wind, another distributed load this way. So there's going to be sets of parallel non-concurrent force systems that are distributed loads. And so if you understand that in any one of these systems you take the area underneath and you stuck it there to get the resultant, but only do that for any single calculation, because as soon as you cut something there, now all of a sudden you've got to recalculate the area and the centroid moves. So understanding that parallel non-concurrent forces is the largest subset you're going to deal with, we're going to be distributed loads. Finally, of course, the problem you've looked at, you'll see again, is probably this one here, pretty common problem, a retaining wall problem. It is a parallel non-concurrent force system. And then you have, of course, a reaction to it, which is no longer a single force. It looks something like this. And so you have this resisting this. Of course, you also would have to have this. And so this is what you're going to see as you start determining and using programs. By being able to divide these larger, more complex problems into different forms of problem, it will help. So these are not just getting you to kind of regurgitate information. It's to get you to start to evaluate what are the smaller, more solvable problems and larger, more complex problems. A typical tower problem, sometimes this is actually a pin joint down here and you have some forces here. Those of you who've done the homework have seen those. This is a concurrent force problem. In this case, the concurrent force problem is obvious because the points of application of the forces are the same there. However, this is also essentially a concurrent force problem because they all have a common point of action, a point of concurrency in their lines of force. So we're going to keep going here so we can get through to the problems and do them. Only I will not put the numbers in here. I will talk when I do those last problems. I will talk about how you go about doing it and how you pull out your scale and stop overthinking breaking vectors into components. Stop overthinking breaking vectors into components. They just break into components, sines, cosines, whatever you're going to do, but in all reality you're just doing what your eye knows that it's going a little bit over and a little bit up, and then when you get into 3D, what you might sense if you know something's coming towards you or away from you. And so a non-concurrent force system, I guess people did a pretty good job on that. In other words, this one and this one, they're concurrent about this force, but this is here. Of course, we remember that any set of non-concurrent force systems can be broken up. So you can break this, can be actually broken up into sets of concurrent forces. So this problem here, of course, could be broken up into essentially that resultant and this one here could be broken up into this resultant, and then these two resultants could be added together to something like that. So that graphic use of non-parallel non-concurrent forces, it's something you should practice and be able to do pretty quickly so you can get a good, by sliding triangles, and we'll get some practice in that as we go through the semester. As we also, of course, just use all this kind of programming is coming. And the reason why it's coming is this. That set of problems that we're given were like this. The first one looked something like this. It was something there, a mass, if you would, with a set of forces here, 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 and they were lined out up to be concurrent force problem. And so how do you need to do that? Well, you just basically figure out, scale off your x and the y, scale off your x and the y, and scale off your x and the y. You make a table, force 1, force 2, force 3, your x and your y, and you add them up. That's a great way to do it if you've got if you're doing a concurrent force problem. Realistically, the best way, of course, to add vectors, I'll just add 3 vectors here. This one plus this one plus this one is to actually start with this one from here to here, transfer this one over, and then, of course, transfer this one down. If those are concurrent force problems, you have the problem solved, and many did that well. You never pull off a number when you do that. The reason sometimes to break these vectors up into components, you'll see in a little bit, is very often they're not going to be concurrent force problems, and you're going to need to break them up into x, y, z, and then x, y, z for something else. All right, so that is how you pull out your scale, and you actually read, and you don't think inches. You measure and put the pounds here and the pounds here. If you're doing that, it might be confusing to mark up actually what the magnitude is. So if you're going to do it this way, there's no reason to actually scale out that vector. That length, that magnitude of that vector is useful if you're doing something like this. But in this case, if you're transferring vectors, right, sliding them in parallel ways, you don't really need to measure anything until you measure your resultant. All right, that was one problem. The next problem was something like this, and get used to this all being the same form of problem. The problem looks something like this. Had a beam and some forces on it, right? Right. Remember, what you'll want to do is you want to generally slide your vectors down, right, if you have it here. And then what you have is radial vector 1, radial vector 2, radial vector 3, and radial vector 4. Once again, you can write out F1, F2, F3, and F4, X, Y, Z. I'm sorry, X, Y, Z, X, Y, Z, X, Y, Z, X, Y, Z. But probably what you wanted to do is to get in the habit of not doing this, but instead doing a table that is the radial vector and the force vector. And so in this case, the radial vector, position 1, 2, 3, and 4, the radial vector will all be x. There'll be nothing in the y, nothing in the z, nothing in the y, nothing in the z, nothing in the y, nothing in the z. Your radial vectors and your force vectors will be nothing in the x, nothing in the y. I'm sorry, in this case, we're not dealing with z. So nothing in the, for the radial vector, nothing in the x. I'm sorry, nothing in the y. So 0, 0, 0. Start that over. We got a couple minutes here, so I'm going to go ahead. Remember that when you lay out your table here, right, you want to write out a radial vector and a force vector table. And you basically have an x, a y, and a z. X, y, and z. That finally gets to the last problem, which is the one that requires that. And the last problem, once again, looks something like this. You have something here. You had a spinny point and you had a bunch of forces, a force here and a force there. You need to write out and break up, if you would. That's the radial vector. This is the force vector. Radial vector 1, force vector 1. radial vector 2, force vector 2. And once again, you just break these into components, break them into components, break them into components, and have a table of the radial vector and the force vector, ijk, ijk, and that is how all these problems are then solved. The definition of moment is r cross f, and you know that the sum of the moments equals 0 in most problems when we're going to talk about, and the sum of the forces equals 0. That's how you solve those problems. Pull out your scale and learn to use it. Thanks for listening.